Now that we understand limits, we're going to talk about differentiation. So the definition of the derivative is the derivative of f at x equals the limit as h goes to 0 of f of x plus h minus f of x over h. We're going to use this definition to drive the formulas of the derivative of various functions. Let's start simple. Let f of x equal x. Then we have f prime of x is the limit as h goes to 0 of f of x plus h, which is just x plus h, minus x over h, equals the limit as h goes to 0. The x's cancel. We have h over h. And there's no problem with h equaling 0 because we're taking the limit. So this just can cancel. We have the limit as h goes to 0 of 1, which equals 1. So that is the derivation of the derivative of f of x equals x. Let's move on to a slightly more complicated function. F of x equals x squared. Then f prime of x equals the limit as h goes to 0 of x plus h squared minus x squared over h equals the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared all over h equals the limit as h goes to 0. Notice that the x's here cancel, so we have 2xh plus h squared over h. Again, h is just going to 0, it's not equal to 0. So the h's here cancel. We get the limit as h goes to 0 of 2x plus h. Now here there's no problem in substituting h equals 0 because there's no dividing by 0. So that just equals 2x. So that we just derive that the derivative of x squared is equal to 2x. We're now going to prove the same thing. We're now going to try something slightly harder, which is f of x equals x to the n. But you'll see that the strategy is still the same. We're going to take the limit as h goes to 0 of x plus h to the n minus x to the n over h. And now we're going to use the binomial theorem to expand this term out. So we're going to be talking the limit over. The binomial theorem says that this term, x plus h to the n, is equivalent to the sum from I equals 0 to n, and choose I as the coefficient, x to the n, h to the n minus I, minus x to the n all over h. Now we're not going to work all of this out. I just want you to notice the first two terms of this sum. The first two terms are x to the n plus n x to the n minus 1 times h plus all terms in h with powers greater than 1. Okay, minus x to the n, again the whole thing over h. Now what will happen is when we, first of all, the x to the n's cancel here, and when we divide all these terms by h, all of these will have powers of h greater than 1, and this will just be nx to the n minus 1, again plus terms involving powers of h. And when we take the limit as h goes to 0, this just goes to 0, and we're left with this. So now we have proved that the derivative of f of x equals x to the n equals n times x to the n minus 1. Now I'm going to simply state without proving some theorems about the derivative. The derivative of a constant times a function equals the constant times the derivative of the function. The derivative of a sum equals the sum of the derivatives. The derivative of a product is a little bit more complicated. It's the derivative of the first times the second plus the first times the derivative of the second. This is called the product rule. Now that we know some basics about differentiation, we can start differentiating polynomials. So, for example, f of x equals 3x squared minus 5x plus 2. We can now use everything we know about the derivative of a constant times a function, as well as the sum of functions to analyze this. So f prime x is the derivative of 3x squared minus 5x plus 2 equals the derivative of the sum of all these functions, which equals the sum of the derivative of these functions. Negative here. Okay, so this is using the sum rule for derivatives, or sum theorem. Now I can factor the constant out, equals 3 times the derivative of x squared minus 5 times the derivative of x. And the derivative of a constant is just 2, because constant functions don't change. And finally, we use the theorem that we proved about powers. So this is 3 times 2x minus 5 times, and the derivative of x is just 1. This equals 6x minus 5. Okay, so we're going to do a simple example of average rate of change. and instantaneous rate of change. So let's assume you have revenue as a function of, let's say, something you're selling, X. Basketballs. Let's say that revenue was 12x minus x squared over 10. So we want to see what the average rate of change in revenue is if production is changed from 100 basketballs to 150 basketballs. So average rate of change in revenue if production changes from 100 to 150 balls. We would just evaluate R of 150 minus R at 100 minus the difference in balls, which is 50. And that's it. That's your average rate of change. So we just plug in whatever that is. 12 times 150 minus 150 squared divided by 10. That's this minus, so all of this minus R at 100. So that's 12 times 100 minus 100 squared divided by 10. And this is all over 50. Now the rest is just computation. Multiply this, subtract this, multiply this, subtract this, and divide it over 50. So I'll have you do that while we set up the next question, which is what is R prime of X? What is the instantaneous rate of change of revenue at 100 cars? So the next question is what is the instantaneous rate of change in revenue at 100 balls? That is R prime at 100, which equals the derivative of R, which is 12 minus 2x divided by 10, which equals 12 minus x divided by 5, all evaluated at x equals 100, okay, which equals 12 minus 2 times 100 divided by 5. Okay, and again, you can calculate that. So you have average rate of change over an interval versus instantaneous rate of change at a point.